Hopefully you got a chance to watch the video and you enjoyed it. And maybe you're glad that we didn't have class, so I couldn't feed these to you. But out of total, we tested 110 Skittles, and of those, 23 were rotten. So what would you say the chances of getting a rotten zombie Skittle is? If you've had a little probability, you're probably thinking 23 out of 110. Or if we write that as a fraction, 23 out of 110, we could change that and divide it to a decimal. It comes out to about 0.21, which is about 21%. But what does that actually mean? How does that help you with Skittles? If you're going to, are you going to play this game? I mean, there's not a lot to win, but it is kind of fun. If you think of 0.21 as being close to 0.2, that's 2/10, which reduces to 1 out of 5. That means you would expect, on average from the whole bag, you would expect out of every 5 Skittles that one of them would be rotten flavored. Okay? Now, depends on who you are. Some people didn't even, in the past, haven't even been interested in this game at all. Some people are like, oh yeah, that's kind of fun. Regardless, here's the probability behind it. All right, there's really 2 kinds of probability. There's what we call theoretical probability and then empirical or experimental probability. The difference is what we've done here, this is called empirical or experimental probability. Because in this case, it's based on the data. It's based on what we've actually done, okay? So you can read that here. Empirical, when performing an experiment, that's the key here. Collecting data, the fraction of times an event actually occurs compared to the total. So the number of actual, it says desired outcomes. In this case, it might have been the undesired outcome of getting a rotten flavor out of the total. So we did 23 out of 110. Now, the theoretical probability would be what the fraction of events should occur in the ideal. So maybe if we knew somebody at the Skittles factory and they told us, for all of the Skittles, for all the rotten zombie flavored Skittles they made, how many were rotten, how many were good, then we would know each bag, in theory, should have a certain percentage. And I don't know that, right? I don't work for Skittles. And so that's the difference between theoretical and empirical. We're going to take a look mainly at theoretical, but we're going to use the empirical to our advantage at times. In the long run, they should match. Let me explain that. Let's say you flip a coin, okay? Pretend it's a fair coin. Actually, this is going to get into the next slide. The sample space is all the different possible outcomes. So for a coin, you've got 2, right? You can either have heads or you can have tails. This is the sample space. Each time you perform this chance process, you flip the coin, that's called an outcome. So an event. Each event is one time of doing this. So if I flip the coin once, that's one event, and let's say the outcome of that event is a heads. Okay? Then let's say you flip it again. Are you guaranteed to get a tail? No. But it likely, 50-50 chance, right? Because the probability, in theory, the theoretical probability of getting a tails is 1/2. There's one desired outcome out of 2 possible outcomes, right? Desired out of possible. All right. And so the theoretical probability of getting a tail is 1/2. But I'm not guaranteed that, right? I might get another heads. And if I do, I could get another heads. Or I could get a tails. Or I could get even 3 heads in a row. That's possible. It could trade off. Okay. But in the long run, you would expect eventually, so I'm going to say as the number of events increases, the theoretical becomes equal to the experimental or the empirical. And so they're related. If you would, what I'm saying is if you would flip this coin 1,000 times, you would expect roughly 500 of them to be heads, 500 of them to be tails. So at that point, the empirical, the data that you're collecting, is similar to the theory. So kind of got long-winded there, but two different kinds of probability, theoretical versus empirical. Theoretical is what should happen in the ideal. Empirical is what actually happens when we start collecting data. And in the long run, those two should be the same. All right. Let's take a look at some probability questions. What's the probability of landing on red? Well, you're probably noticing these pieces of the pie are all the same size. Red is 1 out of 6. And you're exactly right. What is the probability of landing on red or green? Pause it if you need to. Red or green, I could either land on the red piece or the green piece. There's 2 pieces out of the 6, so that's 2 out of 6. What's the probability of landing on red and green? How do I land on red and green? To land on red and green, I would need to land right on the line. And that is possible. Well, you could say then you're not on red or green, you're on the line. I would argue for 0% or really close to 0% for this problem. Okay? I'm making this up. I have no idea what it is, but it's going to be really small. And so that is, let me ask you a question. Is this theoretical or is this empirical or experimental probability? Hopefully you said theoretical because this is all in theory. We haven't actually spun a spinner, but in theory, there's 6 equal places. It should land on the same place or have equal likelihood of landing in each section. All right, let's take a look at this next one. It says compare the 2 spinners below. This is class activity 16A. If you actually want to do this, you could take a pencil and put your tip of your pencil right here and then put a paper clip around that. And what you'll find is if you can spin it, it'll actually spin around like a spinner. And so this is a fun thing you can do with elementary students, if you'd like. But if you spin it, which spinner is most likely to point into a shaded region? Young kids might think, well, this is 2. Well, young kids are probably going to think about this more in common sense, but they might think, well, there's 4 sections here, and there's only 2 sections here. So I've got a better chance here because I have more sections to land in. But if you look at the number of possibilities, there's 6 possibilities here and 3 here. And so when I reduce 4 out of 6, we see the probability in theory is the same on either one. So, which is most likely? They're equally likely, it would be my answer. All right, now we have 2 spinners, okay? This one's kind of a strange shape, but it asks which spinner is the paperclip that spins around the pencil point held at the indicated center point most likely to land in a shaded region? So am I more likely, if I'm going to put a spinner here, to land in the orange? Or is it more likely that I would land in the green? What do you think? Pause it if you need a second to think. You might be tempted to say there seems to be a lot of white space over here compared to the green. So you might be tempted to say this has a better chance, okay? But here's the deal. It's not about the space, it's about where the spinner is spinning. And if you can imagine the spinner going around the circle, in both cases, the spinner has 360 degrees that it can go all the way around the circle. And both shaded regions have the same angle here. They're both 90 degrees. So, here again, it's equally likely in both cases. One last question, and then we'll move on. It says to draw a 4-color spinner, red, green, yellow, and blue, such that the following things hold. Landing on green is twice as likely as landing on red. Okay. So let's say this is red. Then landing on green has to be twice as likely. I'm going to try to draw these to be the same size sections. Are those similar? I feel like the green ones are a little bit smaller, but you get the idea. That's supposed to be twice as much. Does that work? Right now, is it twice as likely to land in green and red? I think so. Now we want yellow to be equally likely as landing on green. So what does that mean for my yellow sections? I need to have 2 of those as well. I don't like this one here. I don't feel like it's in the right spot. Something like that. Can't see that very good. And then landing on blue is more likely than yet landing on yellow. Well, I'm just going to make the rest of this all blue. Determine the probabilities of landing on each of the colors on your spinner and explain your reasoning. Wow. All right, so I think I just kind of got lucky here. So blue looks like it's about 50%. I'm going to make it 50%. And then I didn't mean to do this necessarily, but you see I have 1, 2, 3, 4, 5 sections here. And the other half. So each of those 5 sections must be 10%. So red equals 10%. Yellow is the same as green, which is equal to 20%. Could someone else make a different spinner with different probabilities? And the short answer to that is yes, they could.